dot product is different. If you take the dot product of one vector dotted with another vector, you don't really get a vector. You get actually a number. So this, for starters, try to explain what it is. It is a product where you take a vector dotted with another vector, and it's a mapping to just a plain old number. And the way it's done is by taking the coordinates and adding the products of the corresponding ones. So let's take a look at a couple examples. Suppose you dot this vector 2, 3 dotted with 1, 2. The way we define the dot product is the following. You take the 2 and the 1, and you get 2 times 1, and you take the 3 and the 2, and you get 3 times 2, and that gives you 6, for a total of 2 plus 6, which is equal to 8. That right there, that's called the dot product. Okay, and there's nothing, you can do it for more than just 2 by 2 or vectors of 2 dimensions. You can do it for vectors of 3 dimensions. All you do is take the first coordinates, 1 times 2, that will give you 2, plus you take the next coordinates, 5 times the 1, that gives you 5, plus the next coordinates, negative 5 times 0, that gives you 0, and your dot product is equal to 7 for that one. Let's take a look at this example. You take the 7 and the 3 and you multiply, 7 and negative 3, you multiply them together, that gives you negative 21. Take the 2 and the 5, you multiply them, that gives you 10, that gives you a total of negative 11. Okay, this is what the dot product is. It's just a way of mapping the product of 2 vectors into a number. Let's take a look at this last one. What happens when you dot a vector with itself? If you take a vector dotted with itself, you just do it the same way we did all the other ones. The 2 times the 2 gives you 4, plus the 3 times the 3 gives you 9, and that gives you a total of 13. And that's what the dot product is. And you may ask, well, that's weird. You might have expected something different, or you might wonder, what is it good for? And it's a really legitimate question. It's really good for a bunch of things. Those are all these things on this cheat sheet that I provided. But before we get to those, let's pause this for a second and take a look at some of the famous properties for dot products. Okay. All right, there are about 4 of these famous properties. I'm not going to go through every single one, but let me just show you a couple to see what they mean and what they're saying and why they're true. This one says that if you dot 2 vectors, v dotted with w, the order really doesn't matter. You could switch them around, and instead of doing v dotted with w, you could do w dotted with v, and you get the same answer. We can try to see why this is so. We could just try it with a couple numbers, and then we could try it with variables in general. So let me just show you an example of what this is saying. This is saying that if you take 2, 3 dotted with, say, negative 1 and 7, you would get exactly the same answer as doing negative 1, 7 dotted with 2, 3. Let's see why that should be true. Let's pretend they're not true. Let's just work on each side independently and see if we get the same answer. On this side, if you dot vectors, you get 2 times negative 1, which is negative 2, plus 3 times 7, which is 21, for a grand total of 19. If you do it the other way around, you get negative 2 plus 21, which is a grand total of 19. It's obvious that they are the same. Then you might think, well, this doesn't really prove it. Maybe we just got lucky. Well, not really. You could prove it in general. Oh, well, this wouldn't be an example. This would be in general. If you have x comma y, suppose that's your v, and we'll say u comma d. Suppose that's your w. You want to know if that's equal to u comma d dotted with x comma y, and you check to see if they're the same or not. This would be xu plus yd And on the other hand, you'd have ux plus dy, and you ask, are those the same? We get a yd and a yd over here. Well, you really have a dy, and you have a xu on this one, and you have a ux. Really, the xu is the same thing as ux is the same thing as xu, because multiplication is commutative for real numbers, and the yd, the dy is the same thing as a yd. So in fact, they are the same. And this shows you that in general, for 2-dimensional vectors, the dot product commutes. V dotted with W is the same thing as W dotted with V. And similarly, you can show the other one. The other one shows the distributive law. The distributive law being applied to dot products. In other words, you take this W, and if you have a dot right here and vectors added here, you could distribute that W in there. So that's called the distributive law. This time I'll just do it with an example with numbers, and I'll let you think about the general proof. Suppose you have 1, 2 plus -3, 5, and suppose you're dotting that with I don't know, maybe 2, 2. We'll make it 2, 3. We'll do it that way, and then I don't have room here, but we'll do it the other way around too, which is 1, 2 dotted with 2, 3 plus -3, 5 dotted with 2, 3, and see if we get the same thing. This would be after it's been distributed. This is saying you get the same answer whether you add these first and then dot it, as distributing and then dotting it. So we'll do it this way first. You got 1, 2, comma, or plus -3, 5. That gives you a grand total of -2 and 7 dotted with 2, 3. So I added these first. I added these two first, and I got that. Now you dot these, and you get -4 plus 21. Of course, that gives you 17. And let's do it the other way around. Suppose you had distributed first and then dotted. Let's see what we get here. We would get 2 plus 6 plus here we would get -3 times 2 is -6 plus 3 times 5 is 15. And that gives you, well, the 6's go, that gives you a total of 17. Exactly the same. This is sort of a good evidence. You would, if you really wanted to prove it, you would follow that up with general letters like this. And that shows you the commutativity property. And you should take some time to understand these other ones. This one says you can pull a constant. Maybe I'll show an example of that one. And the other one says that the dot product of any vector with itself is greater than or equal to 0. Let me do this. I'll do one more of these. This one says that u dotted with a constant times v is the same thing as pulling the constant. You pull the constant and you just dot the u times the v. Worry about these things separately. Let's see an example of this. Suppose you had 2, 3 dotted with a scalar. Let's just do scalar 5, 1, 2. That's supposed to be the same thing as if you take the scalar and pull it outside and you dot the 2, 3 with the 1, 2 separately. Let's check. Suppose you keep the scalar outside for just a second. If you dot 2 and 1, that gives you 2 plus 3 times 2 is 6. That gives you a total of 5 times 8 for a grand total of 40. Doing it the other way, where you have a scalar here, that will give you 2, 3, and you scale that vector 5 and a 1, 2, and that will give you a total of 5, 10. That will give you a total of 5 times 2 is 10. 3 times 10 is 30, grand total of 40. It's not an accident. In general, you can always pull this constant. This just kind of shows you how it works, but really you could take some time and do it with generic, variables here like x, y, and a, b, and you'll see everything works the same. this scalar can, if you're dotting a vector with another vector that's being scaled, you don't have to worry so much about the scalar. You can just pull that outside, pull it aside, carry on the dot product, and then multiply by the scalar at the end. Okay, both that and those are the same thing. That's what that property says. That's these properties right here. What we want to do after this is maybe check out some of these other ideas and see. The very, very important question is, what in the world is this good for? What has it done for us lately? So let's put this on pause for just a second and come back and contemplate that question. So one of the first things that the dot product is good for is to find magnitudes of vectors. We've done this before, and it's worth taking a look at here in a different point of view. From a different point of view, take the vector v, which is, say, 2, 7. And suppose you want to know the magnitude. How big is it? In the old days, what we would do, or prior to today, what we would do is you try to graph it, and you think, all right, this vector goes over 2 and goes up 7. So the vector v is right here. That's my v. To figure out the size of it, I would just go like this. The size of v is equal to the 7 square plus a 2 square, and then I would take the square root. Right? That's a normal way to find the size of the hypotenuse on a right triangle. By the way, this is the square root of 49 plus 4. That would be the square root of 49 plus 4, which is equal to the square root of 53. That's fine. That's what we did before. The dot product has a different idea. It says, you know what, we can do that using the language of dot products. What happens when you take v dotted with v? Well, that would be 2, 7 dotted with 2, 7. That would give you a grand total of 4 plus 49, which is also 53. It's the same thing, taking the 2 square and the 7 square. So in some sense, you could think, well, anytime you take the vector v and dot it with itself, you get 53. Or you get the size of it squared. So you could rephrase it this way. A vector dotted with itself is equal to the norm of the vector squared. And that's the first famous use of the dot product. It's a really clean way to figure out the size of a vector. Maybe I can do one more example of this, or maybe a couple more examples. Suppose that we have, I'll just do an easy one and a slightly more interesting one. Suppose you have w, which is equal to -3 and 2. And you want to know, how big is w? What is the norm? Well, you'd go like this. You could say, well, the norm squared is equal to w dotted with w. Therefore, it's equal to -3, 2 dotted with -3, 2. And that would be equal to 9 plus 4, which is equal to 13. So the norm would be equal to the square root of 13. Okay, that's a simple example telling you that, or explaining that every time you want to find a norm, all you do is dot the vector times itself and then take the square root. Here's a slightly more interesting example. Suppose that you're in 3 dimensions. Suppose this is your x, your y, and your z. And suppose your vector is, I don't know, over 2 spots on the x, maybe 1, 2, 3 on the y, and maybe 1, 2, 3, 4 up. So your vector is pointing that way. You could think about it as 2, 3, 4. And you want to know, how big is that vector? Let's give it a name. Let's call it u. How big is it? Well, the dot product says piece of cake. All you do is take your u. To find the norm squared, all you do is take u and dot it with itself. So that would be 2, 3, 4. Dotted with 2, 3, 4. And that would be equal to 4 plus 9 plus 16. Which would be 29. So the norm square is equal to 29. Therefore, this guy must be the square root of 29. That is, the norm of u is equal to the square root of 29. You see, the dot product is really, really powerful for finding magnitudes. It's not limited to 2 by 2s or even 3 by 3s. You could take a vector that has dimension 10 and figure out how big it is, the size. Just like that, by taking the dot product of it with itself and then taking the square root. That's the magnitude. Here's another nice application for the dot product. It helps you find the angle between two vectors. Suppose you just simply start off with a problem like this, where you've got two vectors and you want to find the angle between them. One way to go about it would be to turn it into a triangle, and you'll use all the ideas from solving triangles from the law of sines and cosines, which is similar to what we're going to do, but we're going to use the language of dot products. So to convert this into triangles, the first thing you would do is you figure out what would this side be over here. Well, let me think. If you join these sides together and say you go this way, then this piece, let me see, will be called x, and w plus x equals v. So I can maybe make a little mental note here. W plus x is equal to v, so therefore x is equal to v minus w. So this piece over here is v minus w. That's this piece. Okay, that's using vectors. Now suppose I, at that point, abandon the vector idea and just go for strictly the sizes of each of the sides. Then I would change this to, the size of this will be exactly the same thing as this side will be the size norm of v, and this side will have the size of v minus w. And then when I no longer have vectors, I just have, you can forget about all those arrows, you just have regular sides, regular triangle. If that's the case, what would happen if you stand on this side right here and apply the law of cosines? What would the law of cosines tell you? Well, the law of cosines would tell you that the opposite squared, that would be v minus w squared, is equal to the sum of these sides squared. So that would be the sum of v squared plus w squared. And that's almost what it would tell you. That's what it would tell you if it was just Pythagoras' theorem. Law of cosines is more general. It considers the case when that was not at 90 degrees. So you have to subtract this stuff over here. 2 times the norm of v times the norm of w times cosine of theta. Right? That's the law of, this is the famous law of cosines. Now that's fine, that's we could have done that in the previous chapter, but what we want to do now is change this using the language of the dot product to see what it says. This guy, any vector dotted with itself can be turned into a dot product. This would be v minus w dotted with v minus w in parentheses. This one, if you turn it into the language of dot products, would just be v dotted with v. This one would be w dotted with w. And this one, you can't do much. Just leave it as norm of v and norm of w times cosine theta. And at that point, it looks really maybe ugly and complicated, but it gets much better than that. You just have to clean it up a little bit. Here we use the distributor property, the one that we learned earlier from the famous properties. You can distribute just like you would if you were foiling. This would be V dotted with V minus W dotted with V minus V dotted with W plus W dotted with W. That's the left hand side, and that's equal to V dotted with V plus W dotted with W minus 2 norm of V, norm of W, cosine theta. Yeah, you may think, well, that doesn't look any better. So it looks pretty ugly, but it gets better. Here it cleans up really nicely. You've got the V dotted with V and V dotted with V. Whatever that number you get there, it can go. Same thing with the W's. They go. Here you can put these two together. V dotted with W, the same thing as W dotted with V. We talked about that one of the properties is commutative. So I get that negative 2 V's dotted with W is equal to negative 2 norm of V, norm of W times cosine theta, for where theta is the angle between them. And it cleans up even nicer here. The negative 2's go, and if I divide both sides by this piece, I get the following famous identity. I get that cosine theta will be V dotted with W all over the norm of V times the norm of W. And that right there is super famous. It's the most professional, the most elegant way to find an angle between two vectors. You just dot them together and you divide by the product of the norms, and that gives you the cosine. Then you can just do a cosine inverse on that. Let me explain that with an example. Suppose you have a vector here. Say this vector is 2, 5. Suppose you have this other vector here. Suppose this is 7, negative 1. And suppose you wanted to find the angle between them. The famous dot product formula tells you that all you gotta do is dot them, divide by the norms, and that gives you the cosine. So if I call this V and I call this W, all I gotta do is go like this. Cosine theta is equal to V dotted with W divided by the product of the norms. So let's figure out some things here. First of all, what would the dot product be for both of these? The dot product would be well, I'll just write out. Well, I'll do it here. 2 times 7 is 14, and negative times 5. Negative 1 times 5 would be negative 5. That's the top. That's the dot product. Okay, I'll do it again. 2 times 7 is 14. Negative 1 times 5. That gives you 14 minus 5. And on the bottom, I need the size of V, which will be 2 squared plus 5 squared. So it'll be 4 plus 25 square root. And the size for this one will be equal to 49 plus 1 square root. So I'm getting that when I plug everything in here, cosine theta is equal to, on the numerator I'm getting 9 all over the square root of 29 and the square root of 50. Okay, this part right here is easy to calculate on your calculator. Then you would just solve that equation, and you get an angle theta, just like that for the angle between them. Let's put this on pause for a second and see what else the dot product brings us. But by the way, when you calculate this turns out to be approximately 0.236, and then when you do the inverse, you get that theta is approximately 76.3 degrees. If you do it in degrees. So that's really the most professional way to find angles between vectors. And keep in mind how powerful this is. You could have vectors in 5 dimensions. Imagine 5 dimensions, and the ease with which you could find the angle between them. You'd be as easy as taking the dot products on the numerator, dividing by each of the norms on the bottom. That gives you the cosine, and you just do the cosine inverse, just like this. Might seem easy in 2 dimensions, but it really is much more powerful in this. In any dimension, you could find the angle between 2 vectors. Okay, let's put this on pause and see what other applications are brought to us by the dot product. Okay, consider the following question. Assuming that we've dominated this formula here, this really nice professional way of finding the angle between the 2 vectors. Consider the following question. What if the dot product was equal to 0? What would this formula tell us if the dot product was equal to 0? Well, it would tell us that this part over here is 0. So it would say that cosine of theta is equal to 0 divided by the size of v times the size of w. Assuming both of these are not 0, then this fraction would be equal to 0. And you would get that cosine theta is equal to 0. And what would that tell you? Well, that would tell you that the angle has to be either, think about the cosine graph, goes something like this. It's 0 at 90 degrees or 270. If you're talking about the angle between 2 vectors, we're talking usually one that's less than 180 degrees. Otherwise, you would measure the smaller one. So this tells us that the angle is 90 degrees. Let me rephrase that again. If the dot product is equal to 0, then the angle is 90 degrees. That's telling you that the 2 vectors are perpendicular. Perpendicular. Such a simple and elegant way to check when two vectors are perpendicular. If the dot product is equal to 0, it's perpendicular. And I think we can handle the converse as well. That would be the following question. What if the angle was 90 degrees? Well, then the cosine of the angle would have to be 0. So then you'd have that 0 is equal to v dotted with w all over the size of v and the size of w. How could it be that 0 is equal to a certain fraction? The only way that could happen is, assuming you don't have 0 in the denominator, is that you have zeros on the numerator. So this would tell you that v dotted with w must be equal to 0. Let me rephrase that. If the 2 vectors are perpendicular, the dot product must be 0. If the dot product is 0, the 2 vectors must be perpendicular. So this is an equivalent, a necessary and sufficient condition to determine when 2 vectors are perpendicular. So you could think about this as a test to see whether or not 2 vectors are perpendicular, brought to you by the dot product. It's real simple. You just check to see if the dot product is equal to 0. Let's check. This one would be 2 times negative 3, that would be negative 6, plus 3 times 2, that would be 6, that's equal to 0. They're perpendicular. You can do it for 3 dimensions. 1 and 3, that gives you 3, plus 2 and 0, that gives you 0. 3 and negative 3 and 1, that gives you negative 3. These are perpendicular. 2 times 1 is 2, plus 3 times 2 is 6, that's equal to 8. That's not equal to 0, therefore it's perpendicular not. Okay? It's simple. If the dot product is 0, it's perpendicular. If the dot product is 0, it's perpendicular. If the dot product is not equal to 0, it's not perpendicular. Just like that. The most simple, professional, elegant test to see whether 2 vectors are perpendicular or not is brought to you by the dot product. That's already quite a few things. Your dot product brings you a nice way to find magnitude. It brings you a way to find the angle between 2 vectors, and it gives you a very nice test to see whether 2 vectors are perpendicular. And there's more. This one is sort of easy, the distance between two vectors. I'll let you read that one. Let's take a look at this one. This is really, really important one, the projection. But before I do that, let me pause this. Okay, so let me try to motivate the next topics. Suppose you're trying to pull an object and you're trying to walk that way, so you suppose the object is on the ground, it's a heavy object. I don't know, suppose you get mad at your computer and you throw it to the ground and you tell the computer, I'm going to treat you like a dog, so you tie it to a leash and you try to drag the computer around. Something like that. You're probably going to be standing such as this and pulling on some leash and pulling on the computer, but the computer's not going to go towards you this way, although you're pulling that way. The computer will probably drag on the ground here. In physics, or common sense would tell you that not all of this force is being used efficiently. Only the part that moves exactly the same in the direction as the motion will be used most efficiently. Or said differently, if this pulling it up is, as far as moving it, does exactly the same thing as maybe pulling it this way, but maybe with not so much force. This vector is much longer, represents a much stronger force, versus if you were to pull efficiently in the same direction of motion, you maybe don't have to pull as hard. That serves to generate the following idea. If I have a vector, any vector, let's call it W, and if I have another vector that's not exactly aligned with this one, suppose it's misaligned or aligned differently, call this V, you want to ask how much of V is really going in the direction of W. How big is the component of V that has the same direction as W? That has a very, very famous name. Well, first of all, you should understand what it is. If somebody draws it like that, you should be able to see that it's this piece right here. It would be this piece right here. This would be the W-ness part of V. And it has a famous name. This is called the projection of V onto W. Okay? The projection of V onto W has exactly the same direction as W, but it has the same size as projecting the little tip onto W. And what we want to do is find out this vector, what this vector is, and you'll see that the language of dot products will be the natural way to do it. This will be some sort of function from dot products. Before we do that though, let me make a little note here. You see that the projection has the same direction as W. So you would, right off the bat, just by looking at the picture, you should note that you would think that this projection should be equal to some scalar of W. Right? It's W may be scaled differently. It's almost like W, but except it doesn't have, it's scaled maybe by a third, or depending on the arrangement, it'll always be a scalar times W. Okay, that being said, let's do the deed here and actually find it. Here's my W. Here's my V. First thing I do is I find a unit vector in terms of W. A unit vector would be the thing I'm going to scale. It would be a vector that runs the same as W, but it has size 1. And we talked about this one before. It's called the norm for W, and it's equal to W divided by its size. That would give you exactly the right direction, the same direction as W, but it has not normal or neutral length. It has the length 1. So these are the important properties. It has the same direction as W, but it has a neutral length. It has length equal to 1. So all I gotta do now is scale this one. Well, how am I gonna scale it? Well, then that's where your right triangle trigonometry comes in. This would be the right scalar. That's how much you want to scale the unit vector. You take this unit vector and then make it the right size. Let's think about that. Suppose we call this angle theta. Let's call this scalar x. Okay, then you could just do some right angle trigonometry. You're standing right here and you find a function that compares the adjacent one, which is x, with the hypotenuse, which if you just look at it as a plane triangle, not as a vector but as a triangle, the size of that is just norm of v. So you would come up with the following equation. You would have to say that cosine theta is equal to adjacent over hypotenuse, which would be the norm of v. So therefore the scalar that you want is equal to the norm of v times the cosine theta. Okay, and you think, well, that's great, but it doesn't look anything. I'm not using the language of dot product. Well, we had already calculated cosine theta using the language of dot products. That one was v dotted with w all over norm of v and norm of w. That's your scalar. So this cleans up nicely because the norm of v's go, and really you just have v dotted with w divided by norm of w. That's your scalar. That's the one we're going to take our normal vector here, the one that has length 1, and we're going to scale it by x. So bottom line is the projection of v onto w would be equal to the scalar times the norm for w. That turns out to be v dotted with w